We've got 8 people watching and 5 people chatting, and maybe the others will come in at some point when they see that it's not so bad. Now, some of you I know, and I know that you're actually pretty good at these, so we're going to be looking at mostly relatively easy puzzles, so I hope it won't be too disappointing. This is being recorded, and so I will be posting it up on YouTube afterwards, after I trim off the nattering at the beginning and probably at the end. But the idea here is to have a resource for people who would like to learn better how to solve these sorts of puzzles. We're going to do a few different kinds, and I decided to focus on the kinds that appear on the Kickstarter page for our new book that's coming out. If you don't know about the book, it's in the description of this session, of this streaming session. There's a link there to it. So there's a few different types of puzzles that are sampled there, and I thought we would start by doing some of those. So the first one, first I want to just talk a little bit about this page again. As you can see, it's full of puzzle types. He has just an enormous number, and they're all in this language that I don't speak, even though I studied it for a little while. But it's okay, because if you just hover over any one of them and look at the bottom of your browser, you can see that this one is Sudoku, and this one is Kakuro, and this one is Slither, but actually it's Slitherlink, and this is Heiawake, and so forth. And so there's a whole bunch of types here, and so if you know the name of the type you're looking for, you can very laboriously just go through that way. Or, Angie pointed out, you could also use Google Translate and see if that works for you. Or I have to say, you could use Bing Translate. That also works. Okay, the one I thought we would start with is called ShakaShaka, which is just about the silliest name for a puzzle type ever. I should be clear. It's this one right here in the corner. So I'm going to go in there. And there are the rules, so you can see it's really very simple. We're just going to go down here to this number 1. And translates to briskly. That's interesting. I don't think I ever attempted to translate it. I have no idea. Okay, so I just like saying it, ShakaShaka. There's a link here just down below each puzzle, and on some of the pages that we'll look at, there will be 2 links here, but this is the one that says V3 in the middle of it. And this leads to this guy's own online solver. And so go ahead and click on that, and we get to a nice page like this with the seemingly odd name Puzzpre. That makes sense when you know that in Japanese R and L are pretty much the same sound. The thing that they have is somewhere between those two, and that they pronounce using like Spanish vowels. So this is actually Puzzpre or puzzle play. And so that's why it's called that, but in English it looks kind of weird this way. So it's a really simple interface, and if you click on parts of a square, it will put up these triangles. That's how this particular puzzle works. And if you click with your right button, unless you're on a Mac and then you're on your own, because I don't know how that part works, right-clicking will put in a little dot, and you can click again to get rid of it. The rules of ShakaShaka are kind of weird, but relatively simple. Your goal, you're going to be filling in these half-square triangles in various places around the grid, never on top of one of the numbers. And your goal is to, command click. Thank you, Joey. That's Joey the Microsoftie, who knows what the Mac interface is. The goal is to fill these in so that all of the remaining white space, is made up of perfect rectangles. And there's one other constraint, which is that any square that's got a number on it, that counts how many triangles are directly adjacent to it. And let me say a little bit about adjacent. So we've got this 1 here. If I put a triangle here, that's not considered adjacent to the 1. This one would be, but this is not and this is not. It's got to actually share one black side with the square. And so we have to have each number has got exactly that many triangles directly touching it. So some things here are not so hard. We look for places that are really constrained. And we'll start here with this 2 in the corner. There's only 2 places where triangles could be, and so we could look at either way for having a triangle here. If I made a triangle like that, it's clear that the remaining white space, whatever the rest happens here, is not going to be rectangular. That's not going to work. And we want all of the remaining white space to be rectangular. So it can't be this, and the only other way to have a place for a rectangle here is like that. And the same thing happens over here. So we've satisfied that 2, and we know that it has to go like this. Similarly with this 3, we know that it has to be like this and it has to be like this, but we don't know on the top. Not necessarily, not yet. It could be like this, it could be like this. We don't know yet, okay? So we'll leave that alone. First most important principle about solving these puzzles. We never put anything in unless we're sure. We don't make guesses, we make deductions. So we put things in when we're forced to put them in, okay? So that's a key rule that we're going to always use here. Now, this part here, these 2 half triangles and this half triangle, those are all white. They're going to stay white, and they have to be part of a perfect rectangular region. That means that whatever this edge to that region, whatever it does, it's going to have to bounce off the edge here. Okay, we're going to have to put in another piece like this. There's no other way that this could turn into a nice rectangle. Okay, so that part's forced. And that makes us look at this square. Right, there's no way to put a triangle inside this square and still have the result give us a perfect white rectangle left over. It's perfect as it is, and there's no way to change it. And so we'll put a dot there to say, yep, that's guaranteed. Got to stay the way it is. Okay. Now, getting back to this proto-rectangle that we have here, if it's going to continue, after it gets to this point, again, it's going to have to make a right angle turn. It can't continue, and the only other way that rectangles work is to make a right angle turn. So it's going to have to go here. And then similarly, it's going to have to finish up. It couldn't turn again because we would have screwed it up over here. Okay? I wanted to point with my finger, but you can see my finger and you can see the screen, but you can't see the 2 of them in relation, so it doesn't work. So we won't do that. So it can't turn in, it's going to have to continue, and there's our first perfect rectangle, second perfect rectangle. So that's all guaranteed. Okay. This 4, we haven't done anything with the 4 yet. It's got to have a triangle over on this side. It could be either like this, which is clearly going to be bad. That's not going to make rectangles. Or like this. So it's got to be like that. We don't know up here. I could make an argument for either direction. So we don't know what to do at that side, just like we didn't know what to do with the 3 here. So we'll leave that alone. This 3 has a triangle to its left, has a triangle below it. Doesn't have a triangle above, it needs one more. It's got to have a triangle over here in the same way as before. It can't be this one, it's got to be that one. Okay. So we can see this edge of this rectangle. Let's go on along. It only has 2 options in all cases. It either continues or it turns at a right angle. If it were going to continue like that, well, there's 2 problems with that. The first is we have a 1 here. He only gets to have 1 triangle, and he's got it already. So we know that this is going to have to stay blank. But even if it didn't, if it went in further like that, there would be no escape. We're going to be screwing up. It's not going to be a perfect rectangle. So we know this is going to have to stay blank. And this is therefore can't continue. It's got to turn like that. And again, on this side, it can't continue. It's got to turn. Now we can see this other principle. We know that this is turning into a perfect rectangle. This side of it is already 2 units long. So this side's got to be 2 units long. This has got to continue like that. It might continue further, but we know that it at least does this. Okay. Well, that gives us another one of these little corners in here. There's no way to put a triangle in there that will leave us with a possibility of a perfect rectangle. It's perfect the way it is. That's going to have to stay empty. Okay. So, we've gotten this far on pretty straightforward deductions. I got a little bit more I guess we could do down here in the corner. Okay, we've got a line here. It's got to turn because it can't go straight. Again, it's got to turn, can't go straight. And then we're kind of stopped. Not clear what we can do with that rectangle yet. Okay. And then again, we have this square, which can't be part of anything. It's too isolated. So it's not on. Okay. I'm now open to suggestions. Anybody see something that they'd like to propose for where we go from here? Okay. We're pausing. Just right of the 3 on the left, says Joey. Yep, so does Keith. Okay, so there's 2 ways that we could put a triangle here. Could be like this, but that leaves us white. There's no way to make it work anymore. So it's got to be like that. So that's great. Okay. Same deal now. Two ways to think about it. One, if it went 2 units on this side, it's got to go 2 units on this side. And the other is, it can't continue, so it must turn at a right angle. And so that, yes, as Angie says, that determines that one. Similarly, now this one can't continue, and so it must turn. And so that goes that way. All right, again, we've got this isolated square here. He's going to have to remain empty because there's no way to fill him in with and keep things from making nasty angles, which means we now know where this one's triangle is. That's got to be over here. It can't be that one. It's got to be this one. It has to bounce off the wall. It has to bounce off the wall. Has to bounce off of this triangle, and we are done. And see, it's very nice. It tells us immediately that we won. And you can even move it around. It's very fancy. Okay. So that's the rules of ShakaShaka. This was a very easy one. Okay, what I'm going to do now is go back in the browser. You can see that was a 1-star puzzle here. And I don't think we want to step up to a huge 4-star one. But let's just scroll down a bit. And here at the bottom, we have a 2-star one, somewhat larger. Let's try that. We'll click on its link. Bring him into view here. Okay. Next principle that I want to talk about when starting these things is, I used, Angie says this is one of the first enigmas she ever saw. Yes, Ada used one of these. I don't remember what the number was. It's in the teens. This does appear in the book. I had at that time never seen a difficult ShakaShaka. They were all really easy, kind of the way that we just went through them, slightly harder. And so when I was putting that one together for the book, I mean, Ada was putting it together. What am I saying? It was an open question. Could I make one that was interesting enough? And so I really poured a lot of effort into it. And I think the people who were on the test solving group confirmed for me pretty quickly that it was solvable. It was fine, but it was not trivial, and everything was good. So that was always my goal. Okay, new principle here. Most important thing to do always is to fill in all the information you've got. People tend to want to say, oh, I can keep that in my head. It's not important. I think it's terribly important to fill in all the information that we've got whenever we can. And we always try to come up with notations for filling in that stuff. So here, we've got these really convenient zeros. Zeros are wonderful. Put in all the dots. The dots say there's no triangle there. Put them all in. Never say, oh, I bet I can remember that. because it's easier to see patterns when all the notations are in there. Okay. We have other things that we know are easy. We have these threes against the side. We saw that before. We know two of the triangles right away. So we have a couple of those. We'll fill those in. Again, we've got lines that hit edges, so they have to bounce. This has to bounce twice. This has to, oops, missed. This has to bounce. And this has to bounce. And oh, look, it's a 1. We've used up its only thing. We'll always, always, always put in the dots. Here's a 4. All of its sides have got to have things. These two we know, because they couldn't be the other way. And we'll stop there. Okay, so that's the part about just make sure that you always fill things in. There's a number of things to go and grab here of different ways that we could make deductions. But the one I like to look at is to keep in mind the rule. All of the white space has to end up making perfect rectangles. So when we look in particular at a square like this one here, if I were to put a dot here and make that be white, we have this irregular white region and there is no way to fill it out and make it into a perfect rectangle. So that can't be a dot. It's going to have to be a triangle. And that's always true when you've got two dots that are around a corner from one another. And you can see that we've got that pattern in spades. It's just everywhere here. Okay, so we know a triangle has to go here. And if you look at the various possibilities, this is certainly not going to make a nice rectangle. Then you'll quickly determine that the only one that will make a nice white rectangle has got to be this way. Now we can look at these little white areas. Here's a white rectangle. We've seen it go along, make a right turn, make another right turn. This side's got to match that side. So we know that we have to have another triangle here, in addition to the fact that this is going to have to bounce off. This line, this diagonal line is going to have to bounce. That forces that to be there. Similarly, in this situation, here's another corner. Fill that in. So that pattern of needing triangles in order to separate dots that are around the corner, it's all over the place. We can just immediately fill it in. Okay? So, we have a number of different possibilities again for where to go from here. Here's one that catches my eye. We have a diagonal rectangle. It's hit a white edge. This is definitely white here. It can't continue, so it has to bounce. So that was nice. We've got this diagonal. He's hitting this wall here. He's got to bounce. It then hits this wall. That has to bounce. It then hits this wall. That's got to bounce. And we're left with this space here. That's going to have to remain white. Okay, we got one of our two for this guy. All right. Let's go back up here. Again, this diagonal line only has two options. It either continues or it makes a right angle turn. If it continued, it would look like that, and wow, that's going to be bad. No way that can work. So it can't continue. It's got to make the right angle turn. It's got to do that. Similarly, this diagonal line can't continue, so it's got to make the right angle turn. And now we can see that this space here has got to be part of this little domino of white. Okay. Here we've got a slightly harder to see version of something we saw last time, a bunch in the previous puzzle, where there's sort of an isolated white square, or unknown square, that's gone off to the side. There's no way to fill in a triangle in here that's going to work with this bit here, and so this is going to have to remain white, which means that this is going to have to bounce off it. Okay. I think that takes care of all of the kinds of deductions that we've seen so far. So, options for where to go next. The one above the 4, says Angie. Okay, that's good. We know that there has to be a triangle here. There are only two options. It's either this one, which starts to look really bad with this, or that one. So it must be that one. So that's great. So we found a place, getting rid of that, whoops. We found a place where we know there had to be a triangle. There were only two possibilities. Finding things is often the hardest part about these puzzles. It's often the case that the deductions themselves are very easy. It's finding them in a big grid that's hard. And so we start looking for areas that are close to a bunch of stuff that feel more constrained, and we focus our attention there and see if any one of them will pop for us. So here it was that we know this triangle can't work, it's got to be this one. Now we're back to our old nice things. We've got this side is 2 units long, so this side's got to be 2 units long, and then it has to bounce off the wall, and there we are. Here's that nice isolated corner. Can't be, there's no way to fill it in that will get a nice rectangle, so this is going to have to remain empty, which is great. Now we know that there's a triangle here. Don't know which way it goes. Both of those look kind of plausible initially. So that's not open. So where's the next most constrained place that we could possibly look to make progress? We need a place that's got lots of stuff nearby, but is not currently known. Below the 1 here, that's a possibility. I'm looking over here where this is really constrained. It's got the 2 crowding in, and that we could try to look here. We don't know. The problem with looking here is it could be like this, or it could be white. And they both look kind of plausible. But you're right, to the right of the 1 is a bit harder. If it's going to be a triangle, it can't be like that. That would make a mess. And oh my gosh, it can't even be like that. Because if it turned, right, it's just going to be, you know, this awful thing. So that can't be a triangle. Well, that's great news. So we know that that's going to have to be a dot, which means there has to be a triangle here. It can only be this one. And now it bounces off of here, and it bounces off of here, and that's all good. Okay, so we found a nice constrained place here, and we were able to make progress with it. This side of the 4 still needs its triangle. It can't be this one, so it's got to be that one. So we look at this point here. We have another one over here. This point thing is actually quite cool. Interesting things happen with points. This line here, it has to either continue or it has to turn. If it continued, it has to look like that. And that, boy, screws up this side of the point. And the same thing applies here. If this guy were to continue, oops, it would have to look like that, and that screws up that guy. So points are actually points of reflection. They don't initially look like points of reflection, but in fact they are. So we know that in both cases, the things coming to that point both have to turn. So this has to turn, and this one coming down has to turn. And that's pretty handy to know. Okay. Similarly with this point that we created down here, neither one can continue, so it's this one here has got to turn, and this line going up here has got to turn. So boom, boom. So it's a point of reflection. Okay, next option. Where shall we go? What can we do? We have one thing that's sort of left over. Yeah, under the top 3, I assume this is the one that Joey was referring to, right? He's got to have a triangle here, and it can't be that one, so it's got to be this one. Oh, you meant the other one and you got lucky. Well, you got lucky, we'll come back to the other one. Okay. All right. So this one up here was highly constrained because of this triangle over here. It's sort of stuck in a corner, which means we've got to fill the corner with that triangle. And that means it's got to be matched on the other side of that big square, and then it's got something to bounce off of here, so it must turn. And that completes that big rectangle up there, that big square. All right, so that was all good. Let's go back. Joey was thinking down here. So I have a problem down here. This 3, we know that the triangle goes here. 2 possibilities. It could go like that, and then this would have to turn. That's all fine. There's a nice undo button down here, by the way. Boom, boom. Or it could be this way and have this line continue, and then it would turn and come back. Both of those look kind of plausible to me. Yeah, right now, as Angie says, both of those kind of work. So let's look hard here. There's one more thing that we sort of haven't noticed. Let's let you ponder for a moment here. Yeah, Joey is right. It's got this 2 right here in the middle, and it's already got its 2 triangles. Somehow we failed to notice that before, get caught up in things. And so we know the other 2 sides can't be triangles. And what does that create? Why, that creates our fascinating old friend, the dots around the corner pattern. Those dots can't be joined by another dot. That would make a non-rectangle. And so we have to fill it in with a triangle. So that's pretty good. Hi, Prua. The 3 on the right side is ready to be addressed. All right, let's take a look at that. So there's 2 different possibilities for this 3. Could either be this way, whoops, or that way. And he says that we can address this. If it went this way, right, so this is a little bit harder to see than some of the things we've looked at, but it's not too bad, especially here where it's easy to erase. If it went this way, then this side of the rectangle would also have to continue, and then this is looking bad. Okay, so we'll erase those. So it must go the other way, which means that this side has to continue. And now this side's coming down is going to bounce off of this white and close off. And now this triangle here is going to have to bounce off of this and close off. And now we have this diagonal which bounces off here, which then bounces off here, and that's all nice. Okay? So that all fell out nicely. Seeing that it was time to, let me just back up to there, go back to where we were, don't panic. I've got redo as well. Realizing that we do have the opportunity now to go and work on that 3. It's always something that's sort of on our to-do list. It's always worth coming back and saying, well, now do I know? What about now? And it's not always easy to tell. And that's one of the things that makes puzzles like these hard, can add to the difficulty rating for a puzzle, is that these things can be hiding. In this case, we figured out, because Prua had already guessed that if we went the other way, it was going to be bad. And so we got this, and that led to this. So that was all pretty good. Okay, so now we're here, and now we've got something else that we can take advantage of if anybody sees it. Yeah, the lowest 2, thank you, Keith. Now he has both of his triangles, and so we have another dot here, which means that this angle has got something to bounce off of. I don't know if anybody else thinks of these things as bouncing, but for me it's bouncing. Hi, Just MN. The rules here are that we're putting in triangles, and we have to end up with the white area being perfect rectangles. All of the white area is broken up into perfect rectangles, and each number is going to have that many triangles touching it, sharing a line with them. You'll see that that's true of everything we've done so far. So that's pretty much the rules there. Okay, and then we're filling in dots on things that we know to be white here. So now we've got this little, very good. Hi, Mellifer. Good to see you. Okay, so we've got this little white square, which is all stuck in its own and no way to fill it in without screwing up rectilinearity, so he's going to have to be that way white as well. And now we have our friend again. You can see that there's a theme to this puzzle. And this is really often the case. It's really nice when you start to solve these things and you start to realize that you may have to work hard at the beginning and then you find some interesting kind of deduction, and you may very well find that that's kind of the theme deduction, and the person who wrote the puzzle is going to find a bunch of ways to pull out that deduction in places you weren't expecting. And that adds to the advantage of it. Okay? Hi, Victor. All right, so now we've got our dots around the corner here deduction. If this was also white, this region would definitely not be rectangular. So it can't be white. The only triangle that will work is that one. That's great. Okay, now we're getting close to the end on it. We've got the diagonal here, which comes down here. It either continues or it goes straight, or it continues or takes a right turn. If it were to continue, it would have to do that and it would be awful. It can't do that, so it's going to have to turn. That diagonal line had to turn. No being awful. You're right, Angie. We are anti-awful here. And because this side is too long, this side has to be too long. Oops, that way. Which means, oh, look, there's another white square revealed. Now this diagonal line bounces off the edge. And because this side is 2, this has got to be 2. So we're like that. All right. Now, finally, well, here we've got another one of these isolated white squares. There's no way to fill in a triangle and make a rectangle with it, so that's white. We have one, we're finally in a position. We've known forever that the third side of this 3 was going to be over here, the third triangle. We couldn't tell for the longest time which triangle it was going to be, but now we know it's not that one. That would make a nasty thing. That would be, what do we call it, awful. And so it must be this one, and then it bounces all the way around, and we are complete. All right, any questions about how any of that worked? And then we'll go and we'll do a slightly harder one. When using pencil, I would fill in half the triangle. Oh, I see. Interesting. So that would sort of be a note that, you'd fill in a quarter of the thing. Hi, Victor. The rules here were very simple. It's a puzzle. We're trying to fill things, and we'll just go and do another one in a moment. The thing to notice about what we did is that all of the leftover regions are white. Oh, sorry, all of the white regions that are left over are perfect rectangles. That was our goal. All we can fill in are triangles, half squares. And the other clue we had is that all of the places there are numbers had to have that many triangles around them. It's a little hard to see now that it's solved. I'm going to go back and we're going to pick off a different one. We've done that one. Sorry, we didn't want to do that one. All right, let's go do this weird thing. Anybody can do these, Victor. They're just a question of having fun. A little practice. All right, so this looks bizarre, and it is. But what we know is we got some zeros. So fill in all the zeros. And then look at that. Zeros for everybody. Lots of white. Okay. So, first thing that I notice is this region here, back here. If this was a triangle, there's no way to fill in that triangle so that I'm going to end up with perfect rectangles out of all the white. Not the given that this is white. So that's also white. So that's nice. Here we have our friend that we learned about just last time. We've got dots around the corner from one another. If this was white, we'd be in trouble. That's definitely not going to be rectangular, so it's not white. And the only triangle that will keep it working is this one. That means this diagonal is going to have to bounce off the edge and bounce off there, and so we have that much. That gave us, we can do that again over here, we can do that again over here, filling in triangles between things. Okay, my attention is now drawn here. Again, we've got this one cell wide protrusion that we can't make any use of. If this was a triangle, there'd be no way to put a triangle that will keep this being rectangular, so that must be white. And that gives us a new rule, which never came up before. We've got part of a region, and we know it must be rectangular, so we can always fill in more. Well, that means that this triangle here is going to have to, this angle had to turn, and so that's all done. And this one here has got to bounce off the white, and it's got to turn. Okay. And oh look, we've just created, it's almost like there's a theme here. We've just created another isolated place. There's no way to fill in a triangle here that's going to keep it rectangular. So that's also white. Good to know. Down here in the corner, we've got more of this. There's no way to put a triangle here that's going to be doing something we like. So that's got to be white, and we can fill that out. Because once we've got this, the only way this is going to be rectangular is to fill this in. And again, we've got an angle that bounces off of it, and then it bounces off the side, so we've got this much. Now, it's a little trickier. This was all the sort of easy part. So, ideas. Where can we go from here? No ideas. People are pondering. Zach, that slanted rectangle in the middle, if it continued upward, it would be bad. Okay, so you're talking about this side of it. Okay, if that continued upward, doesn't look awful at the moment. Oh, but look at this. There, that's what you were pointing out. If this continued up like this, then it leaves this little region. We know that these one-cell isolated regions end up having to be white, and that would be bad. So we know that he doesn't continue up, he must turn. Good job. Okay. That helped. Next. Similar with the lowest triangle. The lowest, you mean over here, Angie? Okay, so if this side continued up, we'd have a white here, guaranteed. It's one step removed from what the other one was, and that leaves us this space, which can't be used by a triangle, so that would have to be white, and ooh, nasty, nasty. There's no way that's going to turn into a rectangle. Backing up, looking at it again. If this continued up, then this space would have to be white. There's no way to fill it in. And that leaves this isolated space, and there's no way to fill it in, so he's got to be white, and now this is badness. Now it's all predicated on this continuing up, so it doesn't continue up, it must turn. And that closes that off. Cool. Next. Second row, column 5, needs to be white. Second row, 1, 2, 3, 4, 5. Okay, so suppose that this wasn't white. Joey has proposed that this must be white. If it wasn't white, it would have to have a triangle. It couldn't be this one, but it could be that one. In which case it would have to bounce off. And I'm just not seeing badness necessarily. Okay. So, all right. So that didn't work out for us. Any other options for folks? Here's a crazy option. Yeah, I think you're right. If we went a long way, Zach, with that deduction, but there are easier ways to see, and I always like to try to find the easier ones. So here's my easier one. Suppose that this square was white, like so. Oh, here, I can demonstrate something cool about this code. We can go into trial mode. Okay, in trial mode, oh, I guess you can't see that button there. Now it's a little bit easier. In trial mode, we're basically doing hypotheses, and it'll help us to undo them all at once. And our trial is, what if that was white? If that's white, then this isolated square also has to be white. And now we know that that's part of a total rectangle, and so all of this stuff would have to be white. And now this is looking bad. Now I can't put white here, because then we'd end up connecting all of this and it wouldn't be rectangular, and there's no room for a triangle to do us any good. And that all came from just filling in one white thing here. So if we reject our trial, poof, just like that, then we know that there must be a triangle here, and it must be that one. It's the only one that can work in a corner like that, which means it bounces off here, which means it bounces off of here, and we made some progress. Okay, so that was a really sort of big deduction in some sense, but it was easy to visualize. Let me just back out of it a moment. You could already see if this turned into this big 3 by 10 or whatever it is, 3 by 8 rectangle of white, then this is going to look bad. And by putting in the 1, we got the extra hop. So that's how I saw where it was going. This is a 3-star puzzle, so it's not trivial to do these things. So you're going to have some tricky deductions. But that got us this. Okay. Now, where from here? Now we know it's a 1 by 8. Great, great. This is what I hoped you'd notice. We've got this rectangle here. We were used to looking at the slanted rectangles, but we have an enormous amount of information from this rectangle. Great. So we know that we have to put triangles all the way down this edge, down this column here. There's only one triangle that can go there, and he has to bounce off. There's only one triangle that can go there, and he has to bounce off. And there's one that can go there, and he has to bounce off. And then that keeps bouncing, and this one here bounces, and we're like this. That 1 by 8 is an enormous help by knowing that we had to fill everything in. Now we have a lot of ways that we could look at things. We have these points. We know that points are places that both sides turn away from. So this has to turn, and that has to turn, and this has to turn, and that has to turn. And this has been a bounce off of here. And that was all it took. So it's a nice little puzzle, a little harder than what we saw before, but it's based on this nice theme of playing around with the white space. And then there was this great reveal of the 1 by 8 rectangle giving us just an enormous jump. Okay, so that's something you can always look for, is, what clever thing has the puzzle creator made for you. All right, that's ShakaShaka. I want to go on and look at some other puzzle types here. And so I'm going to back out a couple of times, back to our wonderful Japanese menu. And then the puzzle type that I want to look at here is called Akari, or sometimes Light Up, and it's this guy here, which you would only know because you can hover over him and look in the corner. But it's this guy right here. I don't speak or read Japanese. I can read the kana, but that's about it. I studied Japanese for a little while, and I know just enough to be frustrated. It says Museum of Art. Isn't that wonderful? Why it's called Museum of Art is a little bit unclear to me. I think it's part of the whole story about having lights that are lighting every part of the museum, and we'll come to the story here. Okay, so I'm actually going to skip this 1-star one, and we'll work on this one first. You can see that there's 2 links here, but we want the bottom link. We want the bottom link for puzzle number 2. It's the one that says V3 in it. And that gets us to our old friend, Puzzpray. Okay, so different kind of puzzle here, even though it looks identical to the ShakaShaka. This is a different kind of puzzle. It's called Akari, or Light Up, And the rules here are that we're going to put lights in some of the squares. Each light that we place will light up its entire row and column until it hits the edge of this grid or until it hits a black square. So if I were to put a light here, you can see it lit up its whole row, it lit up its whole column, but it stops when it gets to black squares. Okay. There are a couple of rules about the placement of the lights. The first rule is that any number is telling you exactly how many lights are right next to it, horizontally or vertically next to it. And the other rule is that no light can be placed somewhere where it sees another light. So if I had that light here, I can't place another light here because these two lights are lighting each other. That's not allowed. Okay? All the lights have to, we have to end up with every square being lit, or it could be gargoyles. Some people think about this in terms of gargoyles. There's no real explanation for why they would think of it that way. But we're going to go with lights this time. So let's just recap the rules. Place lights. Every place it has to be lit. Every place has to be lit by at least one light. Lights can't light each other. And the numbers tell us that there must be that many lights exactly adjacent to the number. Okay, so as Prua pointed out, yay for zeros. We know, again, right-clicking here gives us the ability to put in these little dots saying, I know there's no light those places, and there's no lights here. And the other thing that's really nice is a 3 on the edge. Boy, he's only got 3 places to put lights, and he's got to have 3. And so we can put lights in all of those places. Great. That solved that problem. He's all done. Okay. And oh look, that gives us already lit 2 of the sides of the one. This one's got to have a light, but it can't go in either of the green places because lights can't light each other. So it must go here. And that makes this one easy. There's only one place for his light. And that makes this 2 easy. You can see that the puzzle maker was having fun. You're just walking around the edge of the puzzle. So this one's only got 2 places to put his 2 lights. It's got to be here and here. That tells us about this one. Great. That was fun. Okay. But now, nothing else works like that. If we look, all of the other ones say, I want this many lights. He wants 2 lights but has 3 places to put them. 1 light has 3 places to put them. 2 lights, 3 places to put them. 1 light, 2 places to put them. What could we do? Okay, now it's slightly harder. Now this is where we get to the second kind of deduction that gets made. Joey says, bottom right one, if you place the light above it, then badness. Okay, let's look at why. That's correct. He says if we placed a light here, it's about this one. He's got only 2 places that he could have a light, either here or here. And that there's one place we could put a light to eliminate both possibilities, here. If we put a light here, we've eliminated both of the ways that this one could have had a light. And so that can't be right. Another place to look is this one. He has 2 places he could put a light. If there was a light here, it would eliminate both of them. And so that tells us that both of these are places we can't put lights. And in both cases, that means that we know there's only one place left for those 2 guys. This 2 then only has 2 places. This one only has 1 place. This 2 only has 2 places. There were some other things that we could have done, which Prua was pointing out one. And we'll get to that in a second. We're about to do a different puzzle that will require somewhat more. But there we go. We'll take a look at some things that are slightly harder, but that was all we had to do here. So the interesting dots here were these places where we could place a light and it would eliminate too many options for some other square. It would just keep it from having enough things. So that was our easy one. And if we go back out here, then the one that I would like to do is actually down a ways. It's this two-star guy down here. It's 18 by 10. It's puzzle number 7. Don't panic. Click the V3 link. There we go. Prua will love this because it's full of zeros. So the first thing I do is go through and put in all the zeros. Lots of zeros. Boy, do we have zeros. Whoa, what fun with zeros. Yes. Make sure I get everything here. Did I miss anything? I missed one. Where did I miss? Oh, yeah, got me there. Yep. Oh, and another one there. I missed 2. My God. All right. Prua, I'm sure, will tell me if I've missed any further, but I think we got them all. Okay. At this point, none of the deduction types that we used in the previous puzzle work for us. That's kind of the theme of this puzzle, is that we can't do anything with it. Okay, none of those things that work. But as Angie points out, now there's places that can only be lit from one place. The one I like to start is down here. This little dot here needs a light, has to be lit, can't be lit from anywhere except here. This is the only place that can light this square, so it must be on. Okay? Angie wanted to start in the top right. We'll get to the top right. I'm sorry. I'm a bottom right kind of guy. What can I say? This white square now needs to be lit and can only be lit from itself. So there we are. This dot can only be lit from one place, up here. Boom. Okay. We've got this dot, can only be lit from this white square. Just working our way up to there. Oh, oops, sorry. 1 second here. Keith points out that my video is a bit too big here. I can fix that. There. Yes, all fixed now. All right. All right, now we have this dot. You want me to back up some? Sorry. There we go. So backing up to here, we have this white square down here that can only be lit by itself. We have this dot here that can only be lit from up here. We have this dot that can only be lit from this white square, or alternatively this white square that can only light itself. Here's a dot, it can only be lit from up here. Here's a white square that must light itself. That was great fun. Boy, that whole East Coast was really easy to go. Now where? Bottom, second row up. You mean here, Angie? Sure, she says. Lots of places, but fine. We'll start at the right side because Pavel's a bottom right kind of guy. Yeah, there's a whole bunch of these. Here's a dot. Only one place it can be lit from. Must have a light here. Continuing along, just that row, we'll come back and clean up. Here's a dot. Can only be lit from right next to it. Here's a dot. Can only be lit from here. And here's a dot. Can only be lit from here. Okay. Now we can go along the bottom row. Here's a white square that must light itself. A dot that can only be lit from this square. A dot that can only be lit from this square. A dot that can only be lit from this square. Moving up to the third row. Here's a dot that can only be lit from above it. Here's a dot that, oh, that didn't work. Oh dear. How about the fourth row? Well, here's a dot that can only be lit from its right. Getting trickier. Where to go now? Third row farthest left. So third row farthest left. Oh, third. I know what third is. I can do this. 4 down, 3 from the right. Oh, it's like third row from the bottom farthest left. There we go. Well, so that one's a little bit tricky. Right? This piece here could be lit by itself or could be lit from up here. So that's not so straightforward yet. Okay? But there are some places we can find. Angie, I think, had something else. 4 down, 3 from the right. 1, 2, 3, 4. This one. Is this what you meant? Oh, other side. 4 down, from the right. You mean the right. Oh, that right. Yes. Okay. 4 down, 3 from the right. Yes, this dot can only be lit from right next to it. So that helps. And then similarly, we can bounce up to here. He can only be lit from next to him. And here's a white square that must light itself. Oh, look, there's some more of these. Here's a white square that must light itself. White square that must light itself. Okay. And then over here, this guy can only be lit from one place, there. And that gave us another white square that must light itself. Okay. And that's created some more help in the middle. Here we have a dot who now we know can only be lit from directly below him. So that does that. Now we have a dot down here that can only be lit from above it. There. White square that must light itself. Okay. Now we can jump into this corner. We've eliminated enough stuff. Here's a dot that can only be lit from one place, to its left. That creates this dot can only be lit from one place, to its left. This dot can only be lit from one place, to its left. And now we are done. Okay, so those are the two key kinds of deductions that we've seen here. The forcing things to not be lights because they would eliminate too many possibilities, which we saw in the previous puzzle, and this one, which was entirely about somebody's got only one place they can be lit from. That's got to be the place. So a great example of purity in design. It doesn't make for a very hard puzzle, but boy, is it clean in its theming here. All right, so let's go back and grab a different one, and I think I had one in mind here. Yes. So I think back up here to puzzle number 3, 10 by 10. Again, use the second link. It's 3 stars, so slightly more tricky, as we saw before. Okay. Prua, any ideas about how to start? My guess is we're looking at zeros. Yeah, let's go do some zeros. Yay, zeros! Okay, so that got us our zeros. There's a few different ways to go here, but there's a few things I kind of want to point out, so I'm going to go in a particular order here. Let's go back to that principle that we saw at the end of the first puzzle. Here we've got a 3. Angie's just telling me the same thing. Here we've got a 3. He needs 3 out of these 4, which means there's only one that's not a light. So the things that are diagonally away from it, if I had a light here, it would eliminate 2 sides of the 3, and that's no good. So we know the same argument applies on all of the diagonals away from that 3. Same thing down on this 3. Okay. And before I did that, let me just leave that off for a moment. Here we have a 2. He's got 3 places that he could put a light. So I can't have a light here because it would eliminate 2 of his 3. He only is going to have 1 that's not got a light. And so I can't have that. So you get diagonals from 2 on an edge at this as well. So putting on all the other things that we had, now some things just fall out. This 2 only has 2 places to go. This 3 only has 3 places to go. This 1 has its light, so that puts a couple of dots in. I thought there was another one that popped out of that structure. Here, Angie points out we've got a 1. It's out in the middle of everywhere, but it's only got 2 places left that could have a light, here, and this square would eliminate both of them, so no light there. Okay? Now, there's another 1 with only one option. There is this one Is that the one that you mean there, Joey? Yeah, I've been leaving this. It's been sitting there in the middle for the whole time, but I wanted to get this other point. But yes, here's a 1 that right from the get-go only has one option. Might as well fill it in. Okay. Now, what's next? Now below the zero, below the lower zero, there's a light here. There is a dot, needs to be lit, only one place to light it from. There you go. Okay. Above the top 3, here's a square that needs to be lit, and only one place it can be lit from. It has to light itself. That's also true here, below that 3. So that was all good. Okay. Anything else? Now here's an example of something where, because of the size of the grid, things can be really, really easy and sitting out there, but we don't notice them. Here's a 1 that's had all of its options except for 1 eliminated. So that's got to be its last option. So that's just sitting there. Okay. Now, things are slightly trickier. Let's look at this 2. Right, this 2 now only has 3 places to go, and 2 of them have to be lit. So once again, our diagonal has to work. It has to be not this one. Right, this can't be a light because it would eliminate 2 of the ways for the 2 to work, and there's only room to eliminate 1 of them. So that's got to be off again. And that gives us a spot in between that has to be lit. So there's that. Okay. The easy things are kind of drying up here. Now we're going to have to do harder deductions. Row 6, column 2 has to be lit, says Joey. So 1, 2, 3, 4, 5, 6. Very good. That's the one I wanted to point at. Yes. So this square, all by itself, has got to be lit from somewhere. And there are 2 possibilities, here and here. So the question is there any place that eliminates both of those possibilities? This square does. If this was lit, this dot would be in bad shape. So this must be not lit. As soon as that's not lit, now this white square has to be lit, and it must do it itself. Okay, everybody clear on that one? That gives us the only thing for this 1 or for this 2. They're both saturated, so this must be off and must be lit from somewhere. That gives us here. That saturates the 3. So he's done. And now this dot here can only be lit from one place, way over here. So that's on. That saturates the 1, so he's off. This can now be lit from only one place. Boom. So that's that. Now this 1 has only one place left to be a light, which is here. And the deductions just start falling. This can only be lit from here. This must light itself. This 2 needs another light. It's over here. And this must light itself. Okay, so the interesting deduction was back here, where Joey spotted this guy here who had only 2 possibilities, and there was one way to eliminate both of them at once. That's a terrifically important principle. You can make quite difficult puzzles where the chain of deductions is very similar to this except longer. Where if I put a light here, that would have this effect, this effect, this effect, and eliminate one of the ways that this other thing could be lit. And at the same time, it has this effect, this effect, this effect, and eliminates the other way to light this square. And so, that must be a dot way over there. And it comes out of this kind of deduction. So this is the very simplest, purest kind of this deduction. or if there was a light here, this guy's out of luck because both of his possible saviors, lighters, is going to be lost. And so we knew that that was a dot, and then things fell from there. Boy, do I love undo and redo. Boy, it's just great. Okay. All right. So that's Akari. There are many, 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 many Akari puzzles out in the world. You can find them all over the place. That gives you a sense of how to go with these. I want to just stop for a second and take a little bit of a philosophy break. Remember what I said early on. There were two key things to do as practices while trying to solve these puzzles. The first is never put anything in as a guess. You can use trial mode. You can, if you're solving in pen, because obviously you're studly, you can use a pencil. You can use some sort of hypothesis mechanism. Say, suppose this was true. Yeah, see, that doesn't work, so it must be false. That's a very useful thing, and we've used that a few ways here. That's fine. But we never just put things in and say, well, I hope it works out. The goal is more or less to have proven by the end that this is the only way it could ever have been. Okay? In a sense, we're going to prove that there's a unique solution during our solving. The second key principle is that we always write notes. We always put in the dots. We always put in the things that convey all of the information that we've got. In online solvers, one of the biggest ways they fall down is that they don't provide me all the ways that I want to take notes about things that I've learned, or they make it really difficult or clunky to do. But with pencil and paper, boy, my paper is filled with notes about what I know about every square. And with easy puzzles, it's not that necessary, but when you start to get tough puzzles, it's absolutely essential. All right, so that was Akari. I'm going to stop with Akari, and we're going to go to one more kind of puzzle here, and that's Slitherlink. One of the better known types of puzzles. Yeah, Angie points out that a lot of the online solvers have other problems with how they resort information and generally try to be helpful in ways that's not helpful. Okay, so we're going to do Slitherlink, which is one of the great classic puzzle types. This has been around for a real long time and is moderately well known among people who do this kind of puzzle. It turns out it's not very well known among the general public at this stage. I have a geocache that is a puzzle geocache in my area, and the way you get the coordinates is by solving one of these puzzles. And practically every comment I get from somebody who has found my cache says, I've never seen a puzzle like this before. So they're really not that well known. But I love them, and they're lots of fun. So I will give you a little hint. The interface to this one is slightly different. It's not just clicking. And we'll come back to exactly how that works. Let me explain the rules of Slitherlink here. This may look like a rather large example, and it kind of is, but I think it'll be okay for us. The rules of Slitherlink are that we're going to draw a loop. The loop is going to go from dot to dot to dot. Every segment of the loop is going to be either horizontal or vertical, so there would be no diagonal lines of any kind here. And it's going to be just one loop. A single loop, never crosses itself, never touches itself. So it's a nice simple loop. And the numbers here on the grid say for each of those squares exactly how many sides of that square are part of the loop. Okay? So how many sides of that square will have segments going along them as part of the loop? There will be no extra lines. There will be no extra, there's not two loops, you can't have one inside the other or anything like that. It's a single loop, and it has to obey these numbers. That's how many sides of that square contribute to the loop. Okay? So, Pruo is ready to start at the bottom right. You mean with the 0? So, let's start with the zeros. The interface here is a little bit strange. in order to mark something as not being part of the loop, to put a little X there, you can just click. And so I'll just do that here and there, just to do that much. And we'll just continue that for a second here. Down here in the lower right where Pruitt wanted to start, now that we know that because this 0 has no lines going around it, that leaves us with this place. If there was a line here, ignoring this 1 just for the moment, if there was a line here, then it would be a dead end. And it can't be a dead end, it's got to be a loop. It's got to go all the way around and bite itself in the tail. So that tells us that this is off as well. And again, we've still got a dead end. If the line came down this way, it would dead end, so there can't be a loop, part of the loop there. So this is a 1. It must have part of the loop in it, and it's only one segment to go. And this is where the interface gets a little weird. You actually have to draw it with your mouse. You actually have to do a stroke in order to get it turned on. So there's that. Okay, now it's only got a few ways to go. I mean, this one here has to go up. This one here has to go up. That gives us the 3 sides for this 3, you see. So we know the last side must be open. Okay, so that's an illustration of the rule that we've been using here. The 3 means 3 of its sides will have part of the line on it. Okay, so this side's no place to go. It must continue up. That's the 1 we get for a cell that's labeled 1. So the other 2 sides can't be. So we must continue up. And this one has no place to go but sideways. Okay, so those are some very simple deductions. So Angie's suggesting a deduction we'll come to in a second, but let me just do some other things that are really simple. Right, this 3 next to the 0, yes. It's one of its pieces has already been eliminated, and the other 3 have to be part of the loop. So we know that that's got to be true, and each side of that's only got one place to go. And there's several things I want to then do in this area. So the 2 is then done, so that part's clear. But let's look at just outside of this angle here. The loop never touches itself, never crosses itself, never touches itself, which means there can't be a line there. And there can't be a line there. And so this pattern of having made a corner should immediately inspire in you, put in the 2 X's. Always, always, always. Okay? Gotta have those 2 X's. And here's a corner and it's missing one of its X's, we'll put another one in. This is a great example of Ada's principle. You've got to put in all the information that you know. Don't assume that you'll remember that there's an X there. Just put it in. Okay. Let's look at some of the rest of this thing. That was the easy... Oh, here we got another 3. I better do that other 3. So that led to this. And now we put the X's around the corners. This 2 is done. That does that. Okay. Those are the sort of trivial deductions. All right. Corners are really interesting. So let's look at this upper left corner all by itself. Do I want to do that? Actually, I'm going to leave that one alone for a moment. Let me come down here because there's a key thing. Wow, that was quite a bong. I think that was Facebook telling me to do something. Okay. This 3 in a corner, I want to talk a little bit about. We know that if there's a line here in the corner, it has to wrap around. And if there's no line, then neither side of the corner has got a line, right? That's just dead-end logic. Well, this is a 3 in a corner. If there's no line going around the corner, then 2 out of the 4 have been eliminated and the 3 won't be satisfiable. So a 3 in a corner is an important pattern. We know that it has to have line around it. Okay. Similarly, for a 1 in a corner, it's exactly the opposite. If we did start to have a line going around the corner, we would be in trouble because it would have to continue around and we'd be using 2 sides and we only get 1. So it gets the opposite treatment, like that. Okay, but let me actually eliminate these two for a moment because I want to talk about this pair of 3s. There's a pattern for 2s in the corner too, but it's a little more complicated, and I will come back to that. This is the most important pattern that comes up all over the place in Slitherlink, is the adjacent 3s pattern. Suppose that there was an X in the middle. Then both of them would have to have the other 3 sides turned on. That's a little closed loop. It's separate from the rest of the loop. We're only allowed one loop. So that's all no good. And it all followed from just putting that X there. That means that when you see adjacent 3s, there must be a line between them. Okay? But there's so much more. Suppose that this outside edge of the 3s was an X. Well, then that 3 would have to be filled in like that. And remember, outside of corners, we'd be filling in X's like that, and now we've messed up the other 3. They can't open outward because it screws up the other side. And so that's not, that must be on, and that's symmetric on the other side. Okay? This 3 parallel line pattern will come up a lot. Whenever you have 2 3s adjacent, you can immediately go in and fill in the parallel lines. It's just a useful pattern that you start to know. There are lots and lots of patterns in Slitherlink, and the very best solvers have sort of libraries of patterns that they recognize, and you'll gain some over time. Okay, so that was one I really wanted to point out. That's the last one for this one, so we know that it goes like that. And that this line has only one way to go, and so that goes like that. And remember, we have an outside corner, so we fill in an X on the outside of it. That resolves the other side. Got a corner, put the X's outside it. This one has to continue as well. This has got only one way to go. This is another pattern. We saw it earlier. We've got 2 X's around a dot on the edge. If a line was here, it would be a dead end. So that's got to be off. And that's 2 sides out of the 2, so this has to continue in, and then it has to continue there, and that does it. We'll fill in all of our X's. And that does it for this 2. So it has to continue. That got that part. Way down here, we also had another dead end on the other side of this 0. So that's got to fill in. The 2 has to do the rest of it. So we need both sides of that 2. And it's only got one way to go. Look at all those corners. Remember to fill in the dots, the X's. When I'm doing this on paper, by God, I put an actual X. Everywhere you're seeing an X here on the screen, I draw an X. Do yourself a favor, draw the X. This has got to continue down like this. Oops, like that. Now we've got this 2, which has left only 2 sides left. Fill in the X's. This 1 is done. XX. This 3, we know it's where its hole is, so line, line. Fill in the X's on the outside. This has got only one place to go. Bink, and then bink. Okay. So, there are lots of options for where to go in these things. But I want to talk about this 1 over here. This is a pattern that you'll see a lot. You have a line going into a 1 that has nowhere to escape. It can't go away from the 1. This one could leave, like that. But the one on the right is going into that 1, and by God, it's going to hit some side of that 1. It's going to do either this side or this side. We don't know which at the moment, but it's definitely one of these 2, which means it's definitely not these 2. So they must be x's. Away from the point where it came in, there got to be x's. That's the line into a 1 pattern. You can see it's all about patterns here. Well, now we've filled in this 3, and this part has nowhere else to go, so that answers that question. The 1 is completed. This has got to continue, bounce, bounce. This has got to continue, bounce, bounce. Look at all those outside corners. Fill in the x's. Okay? So, we have another instance of that pattern here. Here's a line coming into a 1. It can't leave it. It can't escape. It's going to have to hit the 1. So these can't be the place where the 1 is filled. It's got to be one of these two. Okay. But in this case, it doesn't immediately lead to anything. Okay. Next thing to notice. Here we made a 3 in a corner. We decided about 3 in corners. It means it has to go into the corner. This is a 3 that's in a sort of new corner. It's effectively got a corner right here. Didn't look like a corner. It's not the corner of the grid. Nonetheless, it's a 3 in a corner. If we made either one of these two an x, the other one would have to be an x because of a dead line. It would make a dead end. And so we instead have to fill this in. Okay, so it's recognizing a 3 in a corner. Similarly, here's a 3 in a corner. It's much less clear. But again, one of its dots has had 2 adjacent sides of it sort of used up. That still counts as a corner. If either one was an x, the other one would have to be an x. And that's too many x's for a 3. So that's a 3 in a corner. Okay. I'm ignoring your point about the diagonal 3 pattern for a little bit more, Angie. I'm going to get to it, I promise. Okay, here's another 1, and it's in a corner. What did we learn about 1s in corners? They must have x's around them. You can't go into the corner and then get out again. That's too many sides for a 1. So we get more x's there. That just created a 3 in a corner right next to it. So part of this is just recognizing this pattern, because these patterns pop up constantly. So that 3 has to go into its corner. Okay. And that brings up a pattern that is very interesting, but different. This line here, it's going into a 3. There's a couple of things that we can learn from that. The first is, I'm ignoring the fact that I can fill in an x off of this 1 for a moment. Let's just pay attention to this line and this 3. Okay. If this line were to leave again, walking away from the 3, our compulsion to fill in x's around the outsides of corners, so let me put this in trial mode. If this went like that, we would have to put in x's here and here, and that's too many x's for the 3. The pattern is we have a line coming into a 3, and the result is it's not allowed to leave. It's got to stay in there. So we have to put an x here. But it's also got another consequence. It's a line into a 3 that's not escaping, of course. It must continue to one side or the other. It must either go along the bottom here of the 1. Obviously it doesn't, but ignore that for the moment. It's a line coming into a 3. It either goes this way or that way. If it goes across, then there's an x below, because that's the corner. If it goes down, then we have an x to the side. Whichever one it doesn't take, we need an x, because otherwise we'd get branching. Okay. So there's an x one side or the other. Even if we didn't know which way this went, we know that one of these two sides is an x. That means the other two can't be the x. They must be on. So a line coming into a 3 gives us two things right away. It can't turn away, and the far side, the opposite corner, must both be on. Okay, and that's all from just having a line going into a 3. Pretty handy. Now we can go and clean up here. We've already, for a long time, we've had a 1 that's had one of its sides done, so the last one has to be the x, and so this has to fill in, and we put in x's around the outside. This 3 has already had its x for a long time. Things have to continue, and we fill in all these x's. This has got to continue, and then it's got to continue. Okay, so over here, we've got more trivial stuff that's now available. We've got 3 sides of the dot are x's. That creates a possible dead end, so that's got to be an x. Now this only has one place to go and only one place to go, so that's all good. Okay, now I'm finally going to get to another pattern. Oh, yeah, sorry, Angie points out, I told you I made such a big deal about the parallel 3's here. And then we've got parallel 3's down here. The result that we had here was that we knew we had to make 3 parallel lines. That was what we got from having adjacent 3's. We haven't done that to these 2 3's. So it doesn't matter that we already know some other things. It's still the case we must have these parallel lines. Okay, and that gives us, that's got to be an x. We've got to put an x outside that corner. So this has to fill in like that. Got to put an x outside that corner and x outside that corner. This has only got one place to go. That's used up the 2, so that's done. This has only got one place to go. This 2 has been used up, so that's got to go like that. That put an x outside that corner. Oh, this 3 is all clear. X outside that. Look, it's our line going into a 1 again. What do we know? It's this side or this side. It's not these 2 sides. That was all good. Okay. I'm going to stop with that stuff for a while. I'm going to finally let Angie stop worrying about this pair of 3's here. Okay, so I talked about the parallel 3 pattern, the adjacent 3 pattern, but there's the diagonal 3 pattern as well. And I'm going to ignore the bottom part here for a little bit and just talk about the top part. So there's an interesting thing about 3 sides of a square. If it doesn't point up, one side or the other, then it must point down. Oops, I really screwed that up. Okay, what I mean is, it will either, some corner of it will either point, let's say, northwest or southeast. And similarly, it'll either point northeast or southwest. So this 3, so you can see this 3, it points northeast and northwest. That's what I'm trying to get at here. Okay, so this 3, either, in particular, it either points away from the other 3 or it points toward the other 3. If it pointed toward the other 3, going into trial mode here, boom, boom, we'd have to fill in x's, and that's too many x's for the other 3. So we reject that. He can't point towards the other 3, he must point away. And so you see this kind of pattern of the diagonal 3's end up pointing away from each other. We don't know exactly what happens in the middle. There are several possibilities. But we know they're going to point away from each other. That's the diagonal 3 pattern. So we got to put our x's around the outside of that corner. We have a dead end on this dot, which gives us a dead end on this dot, which uses up that 2, tink, tink. Got another corner to put an x out there. Okay. So, lots of patterns. Trying to make sure there's nothing really trivial. Here's one of our patterns again. A line going into a 1. It's one of these 2, so it's not the other 2. Okay. All right, before I get to that, let's finally talk about the final corner. I talked about 1 in a corner, I talked about 3 in a corner. What about a 2 in a corner? Well, the nice thing about the corner is that the 2 lines that are in the corner, the 2 possible edges that are in the corner, are linked. They're either both on or they're both off, because there's no place to go for either one. Either is a dead end that travels around the corner, or it is a line that travels around the corner. For a 2, that means that either it points into the corner, or both of those are x's, so it must point out of the corner. So it's either in or out. There's a little bit more that we can get out of 2's too, but I'm not going to get into that just this moment. So it points either into the corner or out of the corner. Now, we were just saying with this 1, we had a line going into the 1, therefore its line is one of these two adjacent things, and so its line is not either of those. And that tells us, oh look, this 2 in a corner can't point out of the corner any longer. It must point in. Pink, pink. Okay. And so he's used up, and we fill in that dotted line, or that dead end there. This has only got one place to go. Puts an X there. Tink, tink. This 2 is used up. Tink, tink. Put our X in here. This is another kind of dead end. Looks a little bit different. We have to have an X there. That uses up this 2. Tink. Fill in our X's. Okay. That's that part. There are lots of different ways we could go from here. Let's see what people see. What are some options for how we go from here? No patterns. Oh, there we go. Third row, final column. Remember that. I'm not sure what to make of that. X on third row, final column. Here? Is that what you mean? The 3 is missing one of its corner X's. Somewhere I'm missing a corner X. Ah, here! That third row. Thank you. Sorry. Okay. Yes, I got that. Okay. That part I got. Still need something. There's a few different ways we could go here. All right, I'm going to pick my favorite. The diagonal 3's. First, look at the 2 in the first column, row 5. Tick, tick, tick. Yeah? Okay, that's good. That's the simpler one. Let's go with yours. I like Joey's answer. Joey wins. Okay. So, suppose that these 2 lines over here connected. If so, we'd have to put X's outside both corners. Bing, bing. And that would be 3 X's around the 2. So they can't connect. Can't have 3 X's around a 2. So we have to put another X there. Now both of them only have one way to go. This is all good. This goes only one way to go. Puts an X in. There's a dead end. There's another dead end. This guy's only got one way to go. Tink, tink, tink. There's another X. There's a dead end. There's a dead end. Okay, that was pretty good. Next. I'm still willing to go in and do mine. I'll give everybody a chance to slide in. Okay, let me talk about mine anyway here. It's these diagonal 3's again. There's some interesting things that happen right here. Suppose this continued straight down. Go into trial mode. We don't have to imagine it. It's good practice for you to imagine it, but let's go into trial mode. If this went down, then it would have to bounce out to here. Both of these are therefore X's because of branching and that, which means that these have to continue like that because these are 3's, and we get this little heart shape, which is its own little loop, which is bad. So we don't want the heart shape, so he can't continue down like that. So this can't continue down. He's got to turn. That puts an X here. That has to continue across. That puts an X here. He's a 2, so this has to do that. Put in our X's. And tink. Okay. Now, Yeah. Angie wants me to do parity. It might be the simplest thing that we can look at here. Notice that this little line of x's here pretty much, almost, but not quite, completely cuts off this bottom area. If I put an x in here, I'll do this in trial mode. If I put an x in there, this region hold down here would be completely cut off. Hi, Tanya. Yes, it's a little bit, we've been going for a while, and so you missed a whole bunch. We're trying to make a single loop, drawing a single loop along here. It's a puzzle. And the numbers tell us how many sides of that square participate in the loop. If you look, you can see that, this 2 has got 2 sides used for the loop. And this 3 has got 3 of its sides used for the loop. That's what we're trying to do. Okay, but back to our point here. Sorry if you came in late. If this was cut off, then this little area here would be completely isolated. Now, isolated isn't necessarily a bad thing, except there's a problem. It has 3 line ends in it, which means there's no way for them to join up without leaving one of them out in the cold. That's right, the numbers are a recipe, Tanya. Exactly. They are the hints. There are clues in this puzzle, like the numbers in a Sudoku puzzle. So, by putting an X here, we cut off this region, and it only has an odd number of lines in it. We call this a parity argument, because it's the word for it. And having an odd number would mean that one of them is going to lose. And we can't have that. Everybody's got to connect to something. And so the effect of that is to say, you can't cut it off, you've got to give me another line. That's a parity argument. If we had cut it off, we'd have an odd number of line ends going down here, and it couldn't work. Okay. So that's the parity argument that Angie wanted me to show you. Okay, let me go back and do it again and show it again there. So this little teeny region right in here is almost completely isolated. There's almost no other way for something to get in or get out. Okay, that's the thing that you look for in a parity argument. And if we really finish the job and we cut it off, if I put an X there, these 3 ends are going to have to make it all work right in this little region. Nobody else can come in to help. Okay? But there's 3 of them. 3 is odd. 2 of them will end up connecting to one another, and the other one will have nowhere to go. It can't leave. It's just going to be dead-ended somewhere. Even without knowing exactly where they go, we know that we can't cut off this region because there's an odd number of line ends there. Does that make sense to you, Melver? Okay, it's an advanced technique. For now, believe me, we don't absolutely need it for this puzzle, but I wanted to show it while we had the opportunity. But by putting this in, now this region, if I sort of draw this boundary here, has 4 line ends, which is even. There's some way for them to marry up that this will all be a continuous line. If there were an odd number of them, one of them will always be left out. So that's what we've achieved there. Okay, so the best I can see to go at this point is to go into trial mode and try something. This sometimes happens. Sometimes you have to do this. So I don't know what the right thing is here, so I will just try something. I'll say, suppose these 2 connected. like that. We'll see what happens. So these have to be all x's, and that's a dead end, so that's an x, so this has to continue in. And then this could go either way, and that all looks plausible. So this is a great example of a failed guess, a failed hypothesis. What we want for a hypothesis is for it to make a problem. No, sorry, Keith is right. I got this wrong. This 2 only, it has to go down this way. And so this is fine. So this worked, which is a shame. I wanted it not to work. Okay, because then I'd be sure. This just says, well, this is plausible, and that doesn't tell me whether to fill anything in or not. This is exactly the thing that Ada likes to talk about of, you don't fill anything in until you're sure. Well, we're not sure. It just kind of seems to work, but it might be wrong nonetheless. So let's try the opposite trial. If we put an x here instead of connecting these guys, well, then this would have to continue. This guy can't go up. If he went up, he'd go up and across, and that would put 2 x's here, and that would leave this as a dead end. So he can't go up. He must go across. That puts an x here and an x here, and that puts an x there, and now this 2 has got too many x's. So this was great. Right, I can't fail when I'm trying to fail, but this time I succeeded in failing. Okay, if I put an x here, then it logically produces an error. So the x can't be there. That's a real proof. So we reject that and we say, yes, that has to be a line. Now we're not even in trial mode anymore. If I put an x there, it leads to failure. So it must not have an x there. Now we can fill in these guys and do that, and this comes down, and then this goes like so, and tick, tick. Okay, so that got us out of that. We are finally getting to one of the most common deductions in Slitherlink, and it hasn't come up in this puzzle until now, pretty much, which is we've got a little loop here. If these guys connected, it would make its own little loop separate from all the rest, and we're not allowed to do that. We want one loop, not 2 loops. And so that says they can't connect. So this has one place to go. This has one place to go. The 2 needs both its second sides. So that goes tink and tink. And there we are in it. And we have solved this thing. And it didn't even let me get in there and put in the last x's. So very sad. All right. So that is Slitherlink. But more importantly, that's a sense of how these puzzles work. You have to go slowly. You have to resist the option of guessing and just moving forward. Thank you, Prua. Couldn't have been done without your help. This is how these puzzles get solved. They're solved by patience. They're solved by being methodical and systematic, and by being disciplined. Yeah, I can now put the x's in. You're right. I'm very happy about that. So Keith wants me to tell you now that if you enjoyed this, then if I got a link for you, here is a link that leads to a Kickstarter for a whole book of puzzles like this, crafted by Ada Lovelace, and it's a wonderful thing. I hope you'll take a look at it. Maybe you'll back us. Thank you, Angie, for already backing us. I know some of the others here have already backed us. Tell people about it. I'm going to be posting on my Facebook page a link to the recording of this video. So if you have friends who would like to hear this recording and get value out of it, you can go there. If you're watching this on the recording, I will, right here, I think will be a link to the Kickstarter, something like right about there. We'll see. And you can click on that. It'll also be in the description of the video. And that's it. Feel free to get in touch with me on Kickstarter, Kickstarter will work fine, or on Facebook at Pavel's Puzzles. Here's that URL, http://facebook.com/Pavel'sPuzzles. And you can go to pavelspuzzles.com as well. So lots of ways to get in touch with me. Tell me what you liked, what you didn't like about the stream, and we'll do more of this in the future. Thanks so much, everybody. Thanks very much for coming. Bye-bye now.